This is lecture 20 of CS147 Computer Architecture Study, and this is the second part of our cache memory study that we have started in the last lecture 19. So in this lecture we will be talking mostly about cache memory structure, cache memory operations, and cache memory circuit, like how the cache memory is implemented. So let's start with the structure. So what we have learned from the previous lecture is there are a couple of key observations. One is that upper level memories are faster, lower level memories are larger, information transfer happens only between two levels of adjacent memory to one to another, and information transfer happens in a block, not a single word, but it's a multiple number of words together are transferred from lower level to higher level and vice versa. And memory hierarchy is transparent to the processor. Processor issues the address to the memory system, assuming it's a single big and fast memory. So from processor perspective, it is still the good old plain memory structure where it issues address, it issues the control signal, and perform read or write. Now the cache, to understand the concept, we need to first understand this concept of blocks first. Let's say I have an n number of address line, like n bit address line. That means I have 2 to the power n address, okay? And let's assume that this memory, what processor is seeing, is a word addressable memory. Okay, so just to make our life simple in understanding. So it is an each address then contain one complete word, okay, and there are 2 to the power n number of word. Now this whole memory, main memory, is divided into like m number of blocks. M number of blocks, each block having k words. Okay, each block having k words. So that means if you multiply m with k, that will become 2 to the power n, right? So here m multiplied by k is 2 to the power n. So that's many word, assuming it's a word addressable memory. Now cache memory is organized into C number of lines, what we call. Okay, so it's called a cache line. And this C is also like it is determined by the cache architecture, like what is the amount of C would be. Okay, but let's say it is already predetermined and it's a number given that, okay, this cache has C number of lines. So what each line contains, of course, each line contains the whole like k words. Each line contains one block. What does it mean? This means, like, let's say this is 32-bit a word, right? A word is 32-bit. So 32-bit multiplied by k, that many bits are stored in one line. And each line, each like group of 32-bit words sequentially represents the sequential words from lower memory address to higher memory address in that block. Okay, so in other words, this each cache line contains entire block of information. Also, C is less than M, right? Because if C is equals M, then we are basically talking about copying the entire main memory to the cache memory, which is not possible. Cache memory is less in footprint compared to the main memory. Let's say main memory is 16 gigabyte. Your cache memory usually in a system is what, like 512 megabyte, maybe 1 gigabyte. I haven't came across, but it may be there. Just search a little bit in the Google and see what is the maximum cache size. But in general it is in order of megabyte, okay, and main memory is in order of gigabyte. So C is very, not, I would say very less than, but C is somewhat less than M. That's the whole purpose of this memory hierarchy and architecting a memory hierarchy, giving an illusion of faster but larger memory. Now each line does not only have the block, but it has certain associated information as well. Mainly a tag, which is important, and some control bits. So depending on the cache strategies and structure architecture, control signal can very well be introduced with couple of one or two such typical control signal, but in real life it has more such control, can have more control signals in it. But tag is important. Tag is to determine if a block is present in the cache memory or not. We'll talk about this in detail, how to determine the tag and what's the purpose of it. But it's mainly an unique identification for a block that can tell if a block is present in the cache memory or if it needs to copy it from the lower main memory to the cache memory. And control bit is to represent various states. Example, valid if the cache line is valid or not, or if it is dirty or not. We'll come across this term again when we explain it in more detail, what is meant by valid, what is meant by dirty, etc. But they are more like representing the state of the cache line, okay? And whereas tag is an unique identification for a block which can tell that if a block is present in the cache memory or not. So let's say block number B of an reference address A is A divided by K, right? A div K. So what does it mean? Let's say like processor initiated a memory access. From its perspective, it's an address and it's expecting a word back. So it issues an address A. From that address, a block address is computed by this operation A div K. A is known for me, K is known for me, K is the number of word in a block. So we can compute B. This is an integer division. So we are kind of associating a division and modulus operation here, that which determines the remainder of a division operation, but this is the quotient of that integer division operation B. Okay. Then cache line index I of a block address is the modulo of B with C. So now B is computed, C is known, so cache line index is computed as B mod C. So what does it mean? This is a modulus operation computing the remainder of a division operation between B and C. So the I result is from its range is 0 to C minus 1. So it will be accessed one of the line, like one of the number, index number comes in the cache memory. And a tag is for each address, unique tag is created by B div C. Okay, so again, this is a quotient of computation operation between B, which is computed by A div K, and now we div it with C, and that becomes my tag ID. Okay, so if you think this A, for a given address A, each unique A, you will have a unique tag associated with that address, which is mainly derived out of the block address of that corresponding access. Like, and since B is unique, A div K, B is unique, B div C, C is constant. So T is also unique for a given address, right? So, or I would say it's not not a given address, but it's kind of a given block. Its T is unique. All right. So adiff k, again to reiterate, adiff k gives a unique block address. Okay. For a unique block address, bdiff c gives a unique tag. So tag is associated with a block. So with this computation, now let's look at the cache memory operation. What happens?